we know the magnetic field produced by a long line of current now, and a magnetic field will exert a force on a current, right? So therefore, if you put two currents nearby, each will produce its magnetic field, and these two fields can interact, which means there can be a force between them. And in the simplest case of geometry, I have two parallel, straight, infinitely long wires, each carrying a current. Let's call this current I1 and that current I2. They're separated by distance A. I want to know what is the force between these two currents. Okay, now you know the magnetic field produced by one of them on the other is like, for example, if this is Y1, this is Y2. Okay, the magnetic field B1 produced by this wire at the location of the other wire, we know what that is. That is in fact constant. Okay, it's uniform for this entire line. It is equal to mu naught I over 2 pi a. We did that before, right? It's a constant force. And if you take a uniform magnetic field, you ask yourself, for this infinitely long wire, what is the total force experienced by that? Well, you're going to get infinity. Okay, you're going to get infinity. So what I'm going to do is, let's look at the magnetic force produced by one wire on a unit segment of the other wire. Okay, or a finite length, right? Finite length. Let's look at, say, from here to there is a length L. The force exerted on this particular segment of length L of the second wire due to the magnetic field of the first wire, how much is that equal to? What you do is you take that B1, okay, times what? Times the current I2, times what? Times L. Remember that? That was the expression for the magnetic force on a finite segment of the current. It's I L cross B. Remember that? I L cross B. L is the vector from here to there, cross B. But in our case, L points this way, and B, using the right-hand rule, okay, using the right-hand rule, you know, it points inward, right? It points inward. So I and B, they're perpendicular to each other. So the magnetic force, first of all, the direction of magnetic force, L cross B, it's like that. And secondly, the angle between L and B is 90 degrees. So the force per unit length, okay, the force per unit length equals what? Actually, not force per unit length. Force over this segment length L equals what? B1 times L times I2. That's it. The angle between vector L and vector I2 and vector B. Vector B1 is 90 degrees. Okay, B1 L I2. Let us this is I1. Okay, this is I1. Let us plug that in. Okay, so it is B1, which is mu naught I1 over 2 pi a times L times I2. I'm going to move that L down here, okay, so that I get force exerted on a unit length of the wire, F over L. What is that equal to? That is mu naught over 2 pi a, and then it's I1 I2. I1 I2. It is proportional to the product of the two currents. That in fact is the force given by Y1 to Y2. Okay. What about the force given by Y2 to Y1 on the unit segment? Why, by virtue of the Newton's third law, you should have to be equal to this, right? And in fact, the fact that we get a symmetrical expression between I1 and I2 is a reflection of Newton's third law at work. Okay, it cannot be I1 squared times I2, for example, because then you break the symmetry between the two forces. Okay, so this is the force per unit length between two current carrying wires. And interestingly enough, when two currents flow in the same direction, you actually get an attraction. Okay, get an attraction. They tend to attract each other instead of flying away from each other. And you can see for yourself easily that if one current flows this way, another current flows in opposite direction, the force is actually repulsive. So it's kind of strange in a sense that you got two current flow in the same direction, you get attraction, but when you have two charges with the same sign, they repel each other, they don't attract each other. So this is something we have to keep in mind. It's a little strange here. Now, how is 1 amp defined? That in fact is a something we can get from this expression. You might think that 1 amp is defined as 1 coulomb per second, but how is 1 coulomb defined? Okay, you say, oh, don't worry, I'm going to figure out the force between two point charges. But guess what? There is no such thing as a point charge, right? So, in the SI system, the way we define a fundamental unit, we have to define it in such a way that you can use an experiment to precisely reproduce that unit. Okay, and it turns out it is easier for us to figure out the force between two long wires. We can figure out the force more easily, and from that we can define 1 amp, and from 1 amp we can go back to define 1 coulomb. So that's how it goes. The fundamental unit is amp, not coulomb. Coulomb, believe it or not, is a derived unit, even though for pedagogical reasons we always define coulomb first and then amp, but in reality the definition goes backwards. How is 1 amp defined? Suppose I have 2 current carrying wires, very, very long wires. Okay, they have the same current, I1 and I2 are equal. I put them separate by 1 meter. Okay, and if I find the force between them, can I do that? Okay, can I do that? Of course I can measure the force between them. Okay, so this is and if each of them carries 1 amp, how much is that force equal to? Well, we can easily do that. Mu naught over 2 pi, what's that equal to? Well, mu naught over 4 pi is 10 to the negative 7, right? So mu naught over 2 pi is 1/2 times 10 to the negative 7, right? Okay, we separate by 1 meter, so A is equal to 1 unit. I1 and I2 are both equal to 1 amp, 1 unit. So the force per unit length would be what? 1/2 times 10 to the negative 7 Newton. Okay, so here's the thing. If I have an infinite long wire, a very, very long wire, another straight, very long wire, separated by 1 meter, and if I find that the magnetic force between them per unit length happens to be equal to 1/2 times 10 to the negative 7 Newton, then I say the current carried by each one of them must be exactly 1 amp. Okay, that's how we define 1 amp. Once we define 1 amp, what about 1 coulomb? 1 coulomb is 1 amp times 1 second. It is the amount of charge carried flowing through a cross section in a second if the current intensity is 1 amp. Okay, so that's how we define 1 coulomb. Okay, as we continue our discussion about how to figure out magnetic field, we're going to pick up a topic that we started earlier in the first sample problem, and that is, we know in the electrical case we can go from Coulomb's law to Gauss's law, and the reason why we did that was the Gauss's law gives us a new view of the electric field calculation using the concept of electric flux. So we were able to calculate electric fields produced by highly symmetrical charge distributions. Okay, if E and B fields are very analogous, then is it possible for us to go from Biot-Savart's law to something equivalent to it, just like Gauss's law can be derived from Coulomb's law, so that we can calculate the magnetic field of highly symmetrical current distribution, such as infinite long wire carrying a current I. Is that possible? Okay, and that's what we're going to investigate in the next half of this chapter. The first thing we want to address is, can I use a net, like a Gauss, you know what that means, right? The Gaussian surface, right? The self-enclosed net. We call it Gaussian surface. We use that to capture electric field lines, right? Can we use the same idea? In other words, a Gaussian net, a Gaussian surface, to capture magnetic field lines. Okay, to capture magnetic field lines. And if that is not going to work, what should we do? Well, first of all, the magnetic field lines are different from the electric field lines. In a sense, the electric field lines can start from positive charge, can actually emerge from this, like a faucet. Okay, you think of water flowing out of faucet, you can think of a positive charge, and then you can also think of negative charge, where the magnetic field, the electric field lines disappear into. These are like a sink. Okay, and you can certainly capture these, field lines using a self-enclosed net. Here you get a positive flux and negative flux. But the magnetic field lines are different. Okay, magnetic field lines, as far as we know, have no starting point, no ending point. Because if you had a starting point, that would be a monopole north, and here will be a monopole south. Remember the case of a current carrying loop? The B field lines produced by that current carrying loop look like this, okay? See, each current, each magnetic field lines are really just loops. They go round and round and round. They have no starting point, no ending point. Okay, now if that is the case, imagine if we try to, if we try to capture that loop with a Gaussian surface. Do you think that's going to be successful? Well, look, for every time it gets out, it must also go in, right? Because it has to be self-enclosed. It doesn't start from somewhere, it doesn't end somewhere. You cannot capture a positive magnetic monopole or negative magnetic monopole because they do not exist. Okay, so looks like a Gaussian surface, a self-enclosed net, is not going to work if you want to capture magnetic field lines. Okay, we have to do something different. Okay, something similar to the Gaussian surface, but something different to capture the magnetic field lines. And we're going to do that in our next lecture, which will give us this new law, which replaces Gauss's law in the case of magnetic case.